So, good morning. So, let's start and with the controlling degrees of freedom. So, I would say, the very first topic. So, till now we have been discussing about like why we need to have precision machines, what are the applications, and I also try to show you some artifacts, some 3D printed components to show how these concepts can help you to better design your systems or any mechanical module to achieve the specification what you have started with. So one of the very important thing is understanding degrees of freedom and how to control them. So control them basically means you need to have some specific degrees of freedom, certain number, certain numbers, and then some of those degrees of freedom needs to be moved. So we put constraints. So basically, in that respect, we say controlling degrees of freedom. So I think everybody would be aware by now. In general, since mostly we have senior undergrads and master's students. So if you have any doubt, just let me know. We need to discuss separately. Otherwise, I think any rigid body, if we take any rigid body, in 3D space, we have the three translations along X, Y, and Z directions. So simply the translations. And then you have the three rotations. So that's what we talk about in general. So any rigid body in space. So maximum degrees of freedom we can have is only 6. That has to be very clear. And if you think otherwise, please discuss. And all these motions means depending on the coordinate frame or frame of reference you assign it to it, I think you can have a couple of motions. But anyway, the complete motion can be defined by this 6 components, 3 rotations and 3 translations. So when most of the time in machines or in any mechanisms, mostly they are planar in nature. And I think most of the kinematics, dynamics we deal with, I think it will be sufficient, and we can build our entire thing on top of that. So mainly we discuss about planar thing in 2 dimensions, and that helps us to understand. And later we move to 3 dimension, 3D space. So when we are talking about planar thing or in 2D, we have basically X, Y translation. So here if you see that, okay, this, if you take this sheet or rectangular block, and if you are simply considering the planar motion, we are talking about simply XY motions in XY plane. So if you talk about motion in XY plane, there are 3 motions possible. So one is this, the translation in X direction, and another is of course this orthogonal to that, Y, and another thing is this rotation. So you are still, the object is in plane, but still it can rotate. So don't forget the rotation part. So XY and the rotation along the Z direction. So when we talk about 2-dimensional space, then the total degree of freedom possible is 3. How we can achieve that in reality, that we will also talk about later. So when we say controlling degrees of freedom, we also mean we are talking about the constraints, right? So how many constraints to put so that we get certain degrees of freedom. So what it says that when a mechanical connection, any mechanical connection you make between certain objects, right? What happens? There will be a relative motion. relative motion between the two objects, and there will be a reduction in degrees of freedom because both will move with respect to each other in certain ways. And that's why, like, certain degrees of freedom, because they can move easily in this space, but moment you connect them, the way it gets connected, it will put constraint on each other. And that's why we say that the object has been constrained, right? So there is one-to-one correspondence between constraints applied object and degrees of freedom removed. So whenever we put constraint, we remove degrees of freedom. Or in other words, what we say, if we connect, if whenever we mix any mechanical connection, there will be certain degrees of freedom removed, or we can say there we have imposed certain constraints. So in 2D, I think very simple way to do that is, so suppose you take all these three examples, but you realize that this rectangular block or this sheet. So this is just a pin. If you put one you just put it here, and then you put a pin here, right? Just tag pin, and another paper you put it and you connect it. What you realize in this case is along this line. So what do we call it? Constraint line. Along this line, in this case, it's along the x direction. You cannot move this object. If you just want to move in this direction, you cannot do that, because it's a putting constraint without tearing it off or without breaking it off, right? So assuming that it's a rigid body. So moment you have a constraint imposed and you define a constraint line, your object, this object will have certain motion, and the motion along this line will be removed, or we say it got constraint. So what will happen, you may say, okay, it can just rotate. So of course the rotation is possible. So where? So that is a question like, what will be the instantaneous center of rotation? This motion is possible because it's orthogonal direction, and this rotation is also possible. So about this axis, but the axis will lie on this line. It can be also along this. It can be so anywhere, depending on how you move it. So there will be combined motion, y motion, and this theta z motion. So similarly, this you can also put a bar and then put a glue, right? Or simply take a pin and can either join with a spherical joint, or in this case you are just putting a hot glue, hot melt and glue joint. You will get the same result. You have motion along this direction and then this rotation. Similarly, if you simply put a post, mechanical stopper, somehow you just put it there and you make a contact. So nesting force is the force required to make this contact always, right? There will be a contact here, and certain force will be required. Otherwise, other direction, it can move easily and then you lose the contact. So whatever we are talking about, we assume that the contact is established all the time, and under that assumptions we talk about. Another thing we have to also understand, what we are talking about is the instantaneous motion at that particular moment, and talking about small motions. So at that point, whether there is a motion possible. So this will be talking about all the time. So we are not talking about very large motions. We are talking about instantaneous motion, right? So what it says, points on the object along the constraint line can move only at right angles to the constraint line, not along it, right? So I think this is very important, right angles. So suppose if I consider this constant line, so hot glue, and then I have an object here attached, right? So just go by normal mechanical definition. So what we saying, along this line is a constraint. So any object, this object cannot move on this line. It's not possible. What's possible is any motion normal to that. That's possible, right? So I think you agree, and that's why, like, suppose if I want, like, just take like an axis perpendicular to this plane, this can rotate also, right, at this point. But instantaneously, what will happen? What you see is only this motion. So what it says, points on the object, any point on the object. So if you take this point, right, point on the object along the constraint line can move only at, so point along the constraint line. So you have to consider these points. It can move only at right angles to the constraint line, not along it. So that's the basic thing you have to understand. One thing it also says that regardless of which constraint devices, so there can be different means. So here you have constraint, you have this pin and this paper, you have this glue and the bar, you can have post, so you can have various means. So we call it constraint devices. So no matter what kind of devices you might use, whether it's ink or the bar or the contact point, right, the remaining degrees of freedom, whatever is there, that will be the same. That is not going to change, right? So basically what you need to understand in this case is constraint line. Whatever devices you are using, what kind of constraint is going to put, and what is the direction. So moment we can figure it out, or moment we know about it, I think that can be easily replaced with any kind of devices, whether it's a contact based or whether it can be joined. It can be welded also. We can have flexure joints as well. So we'll talk about it. So the body will have a rotational degree of freedom intersecting the constraint line and perpendicular to the plane of the 2D body, and a translational degree of freedom T perpendicular to the constraint line. So these are the directions you have to just figure it out. I think to me it might be very obvious, but I think if you are not able to, just try. And these things are very easy to try, because you can just have a tag pin and just fold a paper and put it, and then just try to have that kind of motion. Again, these 2 degrees of freedom, whatever is available in this case you have the translation along y direction and the rotation above. So these 2 degrees of freedom are independent of each other. You can independently provide those motions. Either motion can take place with or without the other motion, right? So if it's happening together, you can say it's a coupled, right? If you can provide it independently and without affecting each other, right? So it's not coupled in that case. But coupled doesn't mean it's not true. Coupled means okay, depending on where you are rotating and where you what point on the object you are considering for the motion, you can have both motions together also. So because these 2 motions can be made independently, the body is said to have 2 degrees of freedom. And that's the reason we are saying degree of freedom. So the normal nomenclature is, whenever we have such scenario, we simply replace it by this symbol and we say C. So we are putting a constraint here. So just putting a kind of R, and then it's also saying that there is a joint, and just saying C. So it's some nomenclature. So certain book. I'm referring to a book by Blanding, Degrees of Freedom and Constraint. I think you can easily find. And so they follow this convention. A constraint can be thought of as a bar with articulating joints. The joints allows motion. So whatever motions is possible, rotations. So that's why we are calling it articulating joints. The bold uppercase letter C is used for saying whether it's a constraint. Another thing we have to also understand about the equivalence. So suppose we just like what it says, that any constraint along a given constraint line. So we are talking about constraint along the x direction in this case, is functionally equivalent to any other constraint along the same constraint line for a small motion. So what we have to always understand or remember is what we are talking about is very small motions. So suppose we are talking about this case. So here we have these pins, this small paper fold, whatever you call it. So it's putting a constraint along the x direction, and this is the constraint line. So this is the system. This is equivalent to this one as well. It doesn't matter if we move this thing on the other side. So we put the other side, but as long as this is along the same direction, x direction, right? Or whether it's the pin is here. So even if we change the connection point, but still we maintain the direction, right? They are equivalent. So talking about the small motion is a true, right? So that is a provide the constraint along the same line. So they are all equivalent. And this concept can be used to design your mechanism or any device, because suppose you want to have this constraint, right? And you come up with this design, but later you realize that it's not going to work, right? So what do you do? Okay, then you try to find some point. So suppose if you find a point here or somewhere else, you just extend it, right? Extend it, and so along the same line right here. So what is important is this constant line. Whether you are connected here, or somewhere here, whether this point is here on the other side, it's the same as long as you are maintaining this, right? So they are all equivalent. What happens if you have two? So you have the constant line, right? By this one. So that's what you have mentioned here. And if you just continue, you have put another constant here, right? Similarly here also. So with this one, what you realize that one might be, even if you remove this one, this is still going to work, right? In this case, as long as you have this nesting force there, you can still remove this one and you will get this constraints or contact established, right? So what happens if you put two at the same time? The problem is they would start fighting, and like now if they are all rigid, now the question is which one is constraining this body? Which one? Whether this one or two, right? Or one or two. So there will be like fighting, and how that fighting happens, we'll talk about it. But whenever such scenarios are there, we call it over constraints. Over constraint means more than what is required. So one is enough, but you put two, or sometimes you can even put three or four. So there will be many over constraints. whether it's a good, right? So what it's saying, in either case, two constraints are competing to control the same degree of freedom, and that is X case. And that's why it's called over constraint. Maybe I'll, it's an individual class. Usually I stop and then ask question, but okay, I think we just proceed. What is the problem? If you have this kind of scenario, like what will happen? So I think in mechanical, what you understand, or in design, one thing you have to understand is there will be some problems, some tolerances, some limitations, always. So when you are saying 5 millimeter, can you produce any component with that specification? It's not possible. There will be always some plus and minus, right? So we define tolerances. So it means when we have this thing, how accurately you can say, okay, I'll place this post touching the edges, but do you think it's possible? It may not be possible, because maybe you can put the pin, but the gap or this width of this sheet, how to control? Can you get exactly? So what will happen? Either it will be small or big, right? If it's a big, bigger than the width between the post, it's going to squeeze the component. So there will be binding effect. Or it will be loose. It means there will be gap left, and then the things can move. So there will be a clearance. So from precision point of view, both are not good, right? Or you have to make very precise components. Even with that, there will be still some kind of tolerances, right? Some number, plus minus certain numbers, right? What is this number? And that will lead to a lot of cost. So what will happen? So what it says, over constraint results in several practical difficulties, and that's what we have to understand. When we do any design in CAD or paper, it can make 25 means 25, but when it comes to a reality, when we start manufacturing or fabricating those components, we'll be having issues. We cannot make anything exact. There will be always tolerance, right? So if the dimensions of the object or the constraint are not just right, the parts will not fit properly, right? Other thing is, they will be either too loose or they will bind or interfere, right? So I think explained here precisely. So we are faced with a choice between parts that have loose, sloppy, or imprecise location, or parts that do not go together because they are too tight or not fit, right? So these are the practical limitations. And what it leads to, one is the cost. How? So if you are willing to spend more money, what we do? Get parts that fit together perfectly, right? How will you do that? Tighten the tolerances, right? Or we can use special assembly techniques such as binding and pinning it in place. But then in that case, what happens? You cannot do servicing, because the moment you take out, you damage it. Another is the stresses. So even if you are able to manage, right? Suppose they fit perfectly, there is another penalty, and that is called build-up and transfer of the stress. What happens if there is a change in temperature, right? What happens if there is a load, right? So since you are not allowing any kind of movement, and is completely constrained, so it will develop some stresses, and that will also lead to failure. So that will be with the more examples later. But putting more may not be good. So what we are trying to emphasize here is, moment we have over constraint or putting more boards than required, or putting contact because many times we have the impression, okay, let's have more. But moment we have more, we have to deal with a lot of practical difficulties, and that will lead to cost and other problems. So you can see one example here. So there is an object A and B, and suppose they are constrained by these two links at point 1, 2, and 3, 4. But what happens here is they are along the same line, right? So what we are talking about is reduced performance and higher cost, or both, right? And that's why what we try to do is we try to recognize that whether there is a constraint, right? And try to avoid. So in this case, what will happen? So if it's too tight, cannot assemble, right? If it's loose, then what will happen? It may not be straight. It will come like this, right? So there will be always an issue. So this motion, we always have. Another point is what happens if you increase this number of constraints, right? So we are talking about one constraint only at that time, this. But what if we have added this, right? So we added, this is not cross, but say, okay, another constraint, C1 and C2. What will happen in that case? So moment you have two constraints. So one constraint for X, this will not allow this, your X motion, right? And this will not allow Y motion, right? So very easy to understand. So if you have an object, so since it's a planar, what I can say, this is X and this is Y. So suppose I put a pin, I can do like this, and I have another pin here, Y direction, right? What will happen? So this will not allow motion along this direction, but perpendicular to that can happen, right? Similarly, along this, there will be no motions. But what will happen? What will happen to this point? So where is the intersecting, right? It can rotate. So your body can rotate about this axis. So because this can move orthogonally, this point can move orthogonally. It means you can imagine that, right? So any point you take, that can rotate, can have a rotation. So perpendicular, it can move, right? So we are talking about instantaneous motion again. So wherever it intersects, the axis passing through that point and perpendicular to the plane, the rotation is possible. This R at this intersection, wherever it's intersecting, right? And that's why we call instantaneous rotation, or it's a virtual point. It can be also. So there is no rotation point there, right? But still it can rotate at that point. So by carefully choosing these two, you can also rotate an object without having a revolute joint there, right? We have the understanding that if you want to have a revolute joint, if you have this object, and suppose if you have this revolute joint, what we understand is, okay, you have to always extend this, and then, okay, you have to define a joint. But now you realize that it's possible by doing this also. So suppose if you want to define a point of rotation here, that you can do, right? So you can provide a pin here, you can provide a pin here, and still you can have a rotation at this point without having any real joint there. So that's why it's called virtual point. So I think this is one example. Like suppose you want to define a latch as R, this arm, try to means you try to insert here in the hole in order to lock it, right? And suppose you don't have a means to provide any kind of feature here, then what you do, you just put this connection, then you have the instantaneous center of rotation here, and then it can rotate at this point, and then you can lock. Of course, what you realize here is at another instant it has moved, so you have another configuration, and this point has moved. This center of rotation has moved, new instant center of rotation, and that's why it's called instantaneous center of rotation. But for a smaller motion, it's always possible to do that. Again, here we talk about equivalence. So suppose what you are interested in is in this case. So suppose if you have this object and then you want to define a point of rotation here, right, at this point. So where it should be. So one way is, okay, what you want is intersecting lines. So this constant line can be like this. So you have this case. But who says that it has to be like this? It can be this also, right? What is important is a pair of intersecting lines. So it can be like this. Now the question is, who is saying they have to be orthogonal? Why they have to be 90 degrees? It can be anything else also, right? So it can be 70 degree, it can be 130 degrees, still intersecting, right? So it means you can have any angle, not necessarily it has to be 90 degree. What is important is it should not be too close to 0 or should not be like 180 degree. Otherwise, what will happen in that case? If it's 180 or this case, suppose this is the point, then 80 means this is the case and the other point will be like this, right? So what will happen? Now this is over constraint, and then it's constraining only along only one line. There is no other line. There is no other line, right? So then it's going towards the over constraint. So this is not acceptable. But as long as this is there, and then suppose you provide a constant along here, that's fine, because it also provides a instantaneous center of rotation. But they are all equivalent. So this is about the rotational degree of freedom. So what it says that any pair of constraint whose line intersect at a given point, right? What he's saying is this is for small motions and where the angle between the constraint does not approach to 0. Thus, an intersecting pair of C's, the constraint defines a disk of radial lines, any tau 2 of which, provided the angle between them is not too small, can be replaced equivalently by 2 ordinary C's. Now the question is here, what happens if they are not like along the same line, but what happens if they are parallel? So those two constant lines, what kind of thing they have to constrain, right? So just bear with me and I'll talk about it. So some more examples, and like here, suppose you have to convey very thin sheets of material, and you need a roller sometimes to get them in place. And suppose this is the desired point through which this roller should be supported. So since the material is passing, you cannot have this going. So what can be done is you can think of this. So you can provide this constraint so that they intersect at this point, right? And then instantaneously you rotate. So it's a virtual point, but just knowing that, okay, if I place this constraint in this way, I'll be able to find this point, and that solve the problem. So what happens if they are parallel constraint, right? So we have to, talking about two constraints and intersecting. So if they are intersecting, it's a here. If they are parallel, what happens? It goes to infinity, right? And rotation at infinity means if your axis of rotation is somewhere there, what will happen? Is equivalent to seeing translation along this direction. So in this case, what will happen if you're talking about x, y, and this rotation? X will not happen because both are constraining. You don't say over constraint here because, okay, one is this motion, but at the same time, what about this rotation? Because for this rotation to happen, so assume that is at infinity, or so not talking about infinity, but talk about some finite rotation here. So for this kind of motion, it has to either, so what it has to do. So suppose I plot a perpendicular line. It has to move along this. This point has to move along this line. But they are constrained, right, by C1 and C2. It means this rotation cannot happen. But this rotation can happen at infinity because this motion is possible. If you take these 2 points, this motion is possible. So rotation at infinity means translation along the perpendicular direction. So in this case, what will happen? You don't have the rotation, but will have y motions. So you have y translation. And many times this concept is used for designing any parallel guidance. So suppose if you want to design something and you just want to move by microns or millimeter in only in one direction, the best way is just to put these two sticks perpendicular to that, and you will get that motion. So this is used in many of the designs. So what is said that two parallel constraints is a special case where constraint line intersect at infinity. And you are talking about equivalence. So any case you check, they are all parallel lines, right? Same axis. Okay, the nature might be different. One is getting compressed and one is in tension. So it doesn't matter whether they are on the same side or one on the other side, or whether there is a gap. What is important is this distance. This distance should not be 0. There should be always a gap width. Then only it can constrain the rotation. If it's 0, then they are collinear and it's a over constraint case. Okay, so I'll try to finish with this one. So we are talking about a planar motion. So till now, what we understood that there are like this is the object, and we are talking about x, y, and this rotation. Putting one constraint, you remove one. Putting another one, you remove one, right? But you will still have the rotation at this axis. But how to get rid of that rotation part, right? It means, of course, there is one possibility. You can also work backwards. I think the idea is, I'll talk about this, but here, what is important is if we to get rid of this rotation at this point. Suppose if I put a constraint, so suppose I put a constraint here, right? Or maybe here also, or here, anywhere. So suppose I put a constraint here, which is not passing through this point. And what I 90 degree. So in order to have this rotation, because if I want to rotate, this point can move along this line. This point can also move under right angle, right? But if I have this constant, and can I move along this line? This is not possible because this is putting constant along this line. So it means the rotation can be stopped by this constant itself. And in other words, what we also try to see is, if we just extend this constant line, these constant lines, and if they enclose an area, right? So it's a isometric, so it's a much better now. So putting a constant here, actually what happens is, suppose it's an orthogonal direction, if you put it, there is no, this translation is not possible. So you stop the rotations. So this will not work. Means this will not allow any rotation. So as long as there is an enclosed area, that will help. Another case is, you also know that if I these parallel lines, right, it will have this motion. So in order to get rid of this motion, I'll just put a constant along this line. That will also help. So actually this 3 is good enough. Now you can try any motion. You cannot do that. So actually another way of looking at it is, so if I take, I consider 1, 2, 3. So how many ICs, instantaneous center of rotation, IC we call it. There are 1, 2. So if I take 1 and 2, there is third one at infinity, right? If I consider 1 and 3, this is the point. If I consider 3 and 2, this is the point. So there are three ICs. So one object cannot have more than one center of rotation at a time, right? Given time. Same thing is happening here also. You have one here, one here, right? Now, what happens if I have like this, so intersecting, right? And then I say, okay, I have another one, but passing through this point, whether this will do anything. It will still have this rotation, and in this case, it's a over constraint design that we have to understand. Okay, so if you want to constrain any object in a plane completely, we need 3 constraint lines or 3 contacts. Right? And what it says, 3 constraints have been applied to the body in a way that reduce the body number of degrees of freedom to 0. So in plane, we are talking about in 2D. So only talking about X, Y, and this rotation, right? So no degree of freedom has been over constrained, nor has any degree of freedom left constrained, right? And that's why you call exactly constrained. So you need to constrain 3, right? 3 motions. There are 3 degrees of freedom, and you put 3 constraints to stop them or to constrain them, and that's why it's called exactly constrained. Right. These are some definition and concept. I think you will be able to appreciate later when we talk about designs and some practical